Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. We are in subsection 2.3.6. This is an example of a proof by contradiction. So, what are we doing with the proof by contradiction? We start with something that we want to show is true. And then what we do is we assume the opposite. Meaning that we assume that this statement itself is false. Then if we can use that idea to say, okay, if this statement is false, that means, okay, so this statement is false. Let's do that. So if P merges to false, then the basic assumptions that we have, if that forces our basic assumptions to also merge to 0 or false, then so minimally assuming this goes to 0, forcing this go to 0, means that the assumptions actually lie below it. Because anytime you have 0 above something, that's actually what forces the thing below it to go to 0 as well. So if you have something above going to 0, then what's below goes to 0. If you have something below going to true, then what's ever above that goes to true, and it's the opposite effect for zeros. So if what's above goes to 0, then that must go to 0. But what does that mean? That means that assumptions lie below P in this case. So if this forces assumptions go to 0, that establishes this arrow, which is exactly what we need, because then that means that assumptions, which we actually know in reality is true, will actually force that to be true. So it's kind of this funny effect. We establish this arrow by looking in the opposite way, 0, and then that will force that to be 0. It's kind of the one way of looking at it. Now, let's actually see how this is going to work. So what we're going to do is we're going to assume that P is false, which is the same thing as assuming that not P is true. And then we're going to see what happens when not P is true. And we're going to see that this implies some kind of statement. Let's just call it E. Okay. We're going to try to get some statement out of this, which we actually know, based upon the assumptions, is actually false. So if we can show that this actually implies something that's false, okay, well, automatically, if this implies something false, false lies above this, which would actually force this to be false, which would make the opposite statement true. Okay, that's kind of the rough idea. In fact, this is the crux of proof by contradiction. You can just simply look at it this way. But let's think about kind of what's happening here. Is in order to make this implication, we kind of had to assume also the assumptions. And in making this assumption, and we're also assuming at the moment that this guy is true. So if we assume this is true, and we assume that all of this lies below something up here that's false, then that actually means that this whole thing is 0, which actually implies, since this is true, that that is 0. So assumptions being 0. So what we've done is assuming that this is 1 is the same thing as assuming this is 0. So assuming that 0, or P is 0, assuming that P is 0, that is, sorry. And so P is 0 means that assumptions are 0. So we can kind of get the setup. But this just shows the equivalence that we're talking about. But what's really important here is just this fact. If we can just so this is all we really need from this. If we can just say, okay, if we assume the opposite is true and we get something false, we're done. That's it. That's all we really need. I mean, I was only introducing this jazz for conceptual sake, just to get with a definition. I keep the definition of contradiction consistent with what I I had up there before. Okay, so let's actually go through that. So that's all we really want to do is we just want to take this, assume this is true, and end up getting something false out of it. So how do we do that? We're going to explore what happens when we assume the opposite. Now, how do we explore? We explore by equivalent definitions or rewriting things in ways, in more descriptive ways, until it becomes clear on what might need to happen. For instance, there are finite positive primes. We could rewrite that as we can list the positive primes as this. Maybe we can use one of the assumptions that every number, natural counting number, can be written as a product of primes. So let's just use that fact if we're assuming it. So that means that all natural numbers can be factored into a product power of primes from this list. This already seems to be a little bit more hairy, right? In fact, the more we write here and describe what everything is and what their definitions are, it becomes, and using our assumptions, it might become more clear what to do. So let's keep going. What does it mean to be a factor? It means that well, one equivalent way of thinking about that is when you divide by it, you get a remainder, and that remainder is 0. Okay, so we take all numbers, and so maybe what we can do is we can come up with a number such that when we divide by one of these guys, we don't get 0 as a remainder. Okay, so maybe what we should do is we should keep thinking about how an equivalent way of writing down what does it mean to have a remainder. This is one way of thinking about it. You can have the quotient, what happens when you divide, times the number you're dividing by the divisor, plus the remainder is equal to the number that you're interested in. Okay, so this actually, whenever you have this set up, r has to be 0, no matter what, is what we're saying right here. But that seems kind of hairy here, right? When you divide, in particular, here's, if we think through it, here's an example of something that might contradict it. In fact, this is where we're getting to. Notice if we take this product P1 times P2 times P3 through Pn, and we add 1, if we divide any of these guys by P1 through P, or if we take this whole thing and we divide by P1 or P2 or whatever, their primes are actually bigger than 1. 1 is not a prime number. If we divide by any of those, the remainder will definitely be 1. That just contradicts it, right? We just found a number that doesn't have any of these guys as factors at all. So what we have just done is we've just shown that that the statement we've just shown that there is a number that contradicts. So there is a number right here that actually contradicts the statement not P. In fact, what we've actually done in finding this number, what we've actually shown is we've actually shown that not P itself is we've shown the opposite of not P, that we cannot just take from that list of P1 through Pn for any n even, because we could always kind of come up with this. So we've actually shown that not P actually proves this. And notice what we've actually assumed, but what is this? Not P, it's actually P. And we've actually assumed P to be false in this situation. So we've actually shown that not P implies something false. Okay, then if you go back to what we discussed before, that was all we needed, right? And you can kind of work through this. This kind of discusses that again. But because if you showed not P implies something false, we've actually now shown that P was true. And so that concludes. So what we did is basically we found something that contradicted our assumption, even, okay, of this being true. So we actually showed P off of not P. So if you assume not P, we actually got to P. So which means we contradicted what we started with, hence the name contradiction. Notice you have not P and P, you have a choice. One of these has to be 0 and one of them has to be 1, right? Well, if the arrow goes this way, which one is 0 and which one's 1? Well, this one can't be 1 because that would make that 0, and you can't have an arrow from 1 to 0, especially if we kind of go up here and look at this right here. These are the only arrows that are possible. You can't have an arrow going from 1 to 0. So that forces us, if we have that implication, this is interesting because what we've just done and all that work, we've actually shown this implication right here. We've shown not P implies P. And so 1 and 0 have to be somewhere. So 1 has to be here and 0 has to be there. So that actually shows that P is true. And we're done with that proof. Thanks for watching.